Professor Waldemar Hołubowski from Silesian University of Technology, and he will tell us about endomorphisms of vector spaces of countable and uncountable dimensions.
Is it okay?
Yeah,
Andrew?
it's okay.
So I can start?
Yeah.
So first, I would like to thank organizers for the possibility of to give a talk at such nice and interesting conference. And my talk will be on endomorphisms of vector spaces of countable and uncountable dimensions. I work usually with infinite matrices indexed by positive integers, and it is connected with endomorphisms of vector spaces, and I consider group of automorphisms usually, and last time also Lie algebras. And what about me something? I am in fact a group theorist. My first contact with non-associative system like Lie algebras was a first semester of undergraduate studies in a course of linear algebra and analytic geometry. And we considered a vector space R in cube over R, three-dimensional space over R with cross product of vectors. And I proved that cross product of vector V by V is 0 and also Jacobi identity. Nobody said me at that time that I work with Lie algebra in fact. Next, I specialized in group theory. My first paper was in group theory, but last time I also work in something greater. I consider any field K, let V be infinite dimensional vector space over this field. We look at endomorphisms. By endomorphism, we denote associative algebra of all endomorphisms of V, so linear transformation from V to V. And we assume also Zermelo-Frankel set theory and axiom of choice. So for any infinite cardinal Aleph sub alpha, we have Aleph sub alpha is greater or equal to Aleph sub 0, the smallest infinite cardinal, and is less or equal to Aleph sub delta, which is dimension of a vector space V over K, and we denote by E sub alpha the subalgebra of all endomorphisms phi, such that dimension of image of vector space V by phi is less than Aleph sub alpha. And for example, if we have I sub 0, so in this case, dimension of phi, of image of V over phi is less than Aleph sub 0, so the dimension is finite dimensional for each operator phi from E sub 0. And some history, the classical results say that all proper, non-trivial two-sided ideals of endomorphisms of V have the form E sub alpha, where alpha is between 0 and delta. For example, this is the famous result of Nathan Jacobson. However, he gives the proof. He gave a proof in more general setting of ring of endomorphisms over division rings, not only for fields, and to the chain of cardinals Aleph sub 0, Aleph sub 1, Aleph sub delta, which is dimension of a vector space corresponds of a chain of ideals, chain of ideals I sub 0, I sub 1, I sub delta. I added here also 0 ideal and the whole endomorphism of V. And this is a linear chain which contains all two-sided ideals of endomorphism of V. And this is the fundamental Jacobson theorem. And when we look at endomorphism of vector space V, we can look at a new operation Lie bracket defined by psi times psi minus psi times phi. And with this bracket and usual addition, we obtain a Lie algebra. We denote it by GLV with small gl, small letters. Similarly, we can look at endomorphisms which are automorphisms, and we obtain a general linear group of this vector space V. And what we can say about normal subgroups of GLV. We consider the general linear group of any vector space. We are interested especially in infinite dimensional vector spaces, and our problem is describe normal subgroups of GLV. And the answer is in a paper of Alex Rosenberg. He wrote the paper, The Structure of the Infinite General Linear Group, published in Annals of Mathematics in 1958. Rosenberg was a PhD student of Alex Kaplansky. And what we can say about result of Rosenberg? First, we introduce some little facts, and first let K star be the multiplicative group of the field K. I mentioned that Rosenberg's describe the structure not only for fields but for every division rings by I restrict to the fields only. And for any infinite cardinal, Aleph sub nu, which is not greater than Aleph delta sub delta, which is dimension of vector space V. Here we should have Aleph sub alpha, sorry. By G alpha, we denote the subgroup of GL, V consisting of all elements of the form identity operator plus A, where A is intersection taken from intersection ideal E sub alpha with general linear groups over V, which we denote shortly by GL alpha. Clearly, GL alpha are normal subgroups of GLV. However, in contrast with the description of two-sided ideals in endomorphism of vector space V, the group of scalars, which is the group which contains all scalar matrices, identity operator times non-zero element of field K, is also a non-trivial normal subgroup in GLV. And it is clear because in case of endomorphism of V, any two-sided ideal which contains identity is coincide with whole endomorphism of V. So in case of group, we have such subgroup normals which are of the form identity plus matrices from this ideal, I sub alpha, and we have additional normal subgroups which are are formed from scalar matrices. And moreover, it is clear that if we take a direct product of scalar matrices and G alpha, such subgroup is always normal in GLV. And the main result of Rosenberg paper, this is theorem B, if N is a normal subgroup of GLV, it says, then either we have two cases. First case, if alpha is greater than 0, here we have the following possibilities. All such normal subgroups are direct products of a subgroup of scalar matrices, and which is abelian, so which all such subgroups are normal in scalar matrices and also normal in whole group GL. And we take a direct product with some G alpha, which is formed from elements identity plus AR plus matrices from A sub alpha. And the second case, the first case, the proof is correct. I checked it a long time, but it was okay. But the second case of this result is such that all other normal subgroups are subgroups of this direct product GL sub 0 times diagonal scalar matrices. And when I try to look at this case, second case, there was the problem. I recall also that in the first case, we have the big ladder, and I show it later. This big ladder is such that here we have GL sub 0, here we have direct product scalar matrices with GL sub 0, and here we have GL sub 1, first cardinal greater than aleph 0. Here we have GL sub 1, and here we have a linear ordered GL sub nu, which is between GL sub 1 and GL delta, and here we have its direct product with scalar matrices, and the maximal subgroup normal is direct product of scalar matrices F and GL delta sub delta, well, which when delta is dimension of V. And so in case 1 we have a big ladder, and case 2, this is in fact a case of finitary transformation. So such transformations of a vector space V endomorphism such that dimension of image of phi of V over phi is finite dimensional. And this case we consider we fix a basis. This is a countably dimensional case if we consider a fixed basis which is linearly ordered in such a way that by positive integer a sub 1, a sub 2, a sub n, and etc. In fact, such operators are in one-to-one correspondence with column finite matrices. And this is in fact first result which has a good proof, and the second result is we should to describe the lattice of subgroups, normal subgroups of GLV, whole GLV, which are contained in this direct product. We have obvious normal subgroups GL sub 0. So we have all finitary automorphisms which have such automorphism which has dimension of image is less than is finite dimensional, and we have a subgroup of special linear subgroup. We look at finite, we look at column finite matrices, and in left upper corner we look at matrices which have a determinant 1, and here we have also direct product with scalar matrices, and the problem is it something in this square? This is in fact the main problem. And in countable dimensional case, if vector space V is countably dimensional, we we consider column finite matrices. This group of column finite matrices indexed by positive integers over K, and we have such sublattice of normal subgroups, and Rosenberg in fact only describe this normal subgroup of this group. And why he do not solve this problem? Because he relate the proof. He gave not the proof, but he said that the result is proven by Dieudonné in famous paper in 1941, when in which Dieudonné introduced a non-commutative determinant, and in this paper, Dieudonné wrote only 3 sentences on subgroups of this group, and these sentences are paraphrased of the situation for finite dimensional group, and in fact are not exact. So we check it, and it follows that Dieudonné in fact do not give an answer. And I also found that, for example, a special linear group of finite row matrices, when we look at I sub 0, then this ideal of endomorphism and corresponding infinite matrix, all non-zero entries are in the some first n rows and can change for other matrices. And if we, in case of groups, we must to add identity matrix to such operator, and we have a general linear group of finite row matrices. Finite rows means that only finite rows of these matrices differs from when we differ from this matrix identity operator. Finite rows are only filled by non-zero entries. And here we can look at a special linear subgroup, finite rows. This means that in the left upper corner we have here a matrix. Left upper corner is a matrix from SL. Here we have identity on the diagonal, and here we have something. And this subgroup was named from was introduced by Kloves and Hirsch in the paper in 1958, and I say more here also that here we have a sin lines and sig lines, and sin line means that the factor group, this factor group by this subgroup is simple, and sig line means that here we can have some normal subgroups. And also one remark: if we have a K, a 2-element field F2, then we have the situation that this scalar matrices, this subgroup is trivial, and GL finite rows coincide with special linear finite rows subgroup. So we have a very, very simple lattice of normal subgroup in this case. And mathematics is beautiful because we have analogs with groups and the algebras, normal subgroups and ideals, and simple groups and simple algebras. And in mentioned paper of Kloves and Hirsch, which was in Mathematische Zeitschrift in 1953, it was shown that this subgroup SLFR is simple group of infinite matrices. And I look at this proof, and it was easy to show that if we consider Lie algebra, which consists of matrices, we have non-zero entries in first row. Here we have 0 below some row, and the trace of such matrix is equal to 0. This is correspondingly algebra of this subgroup SLFR. Then this algebra is simple, and in case of any field of characteristic 0, it was shown in my paper in linear algebra and its application, and was generated with my PhD student Sebastian Żurek to other fields of other characteristics. We also can say that, in fact, Baranov uses Kegel local cover theory in locally finite groups, also describes simple Lie algebra of finitary transformation endomorphisms. However, this proof is much more complicated, and we give very, very simple proof, which is formed by direct computation and is understood for students from the first semester. Our proofs are very elementary. Now I can say about second paper, which was motivation for our research. Ivan Penkov and Vera Serganova, in this paper on Terson representations of Mekili algebra and their then subalgebras, announce result that in algebra of column finite infinite matrices we have only 5 ideals. And I and my PhD student Sebastian Żurek, we try to check this proof, because this was only announcement without the proof. It was remarked, and result appeared in Journal of Algebra in 2023. And what we can say about the latest of ideals in algebra, the algebra of column finite matrices over a fit K. We have the following figure, and Penkov and Serganova said that GL column finite, algebra of column finite matrices, has 1, 2, 3, 4, 5 non-trivial proper ideals. We, in fact, in our papers, check this situation in at a lot of ideals which are connected with, which are indexed by elements of a field, non-zero elements of the field, and in fact we can check this algebra has codimension 1 in this algebra. This algebra has codimension 1 in this algebra, and these algebras also are linear, are Lie algebra of codimension 1 in this bigger algebra. And the general case, because here we restricted to column finite matrices, was considered in my paper with Oksana Bezuszczak and Bogdana Olinik, which appeared in Proceedings of AMS in 2023. And we have a great lattice of ideals, and this sublattice of ideals which are in direct product of scalar matrices and GL sub 0. This lattice is very similar to the lattice proven in countable case. We have also a big lattice which is under GL sub 0, and here we can have many such rank of ladder with scalar matrices plus GL sub mu, and here GL sub mu, such a range. And going back to groups, I also look at the following problem: how to fill the gap in Rosenberg papers. So describe all normal subgroups here, and after giving the answer to algebras in this countable case, confinite matrices, it was much easier to consider the case of groups. And in the paper by mine and my student Maciaszczyk and Sebastian Żurek, which appeared in 2022, we have the following complete answer. And here, if H is a normal subgroup of this direct product, scalar matrices and general linear group of finite row matrices, which contains SLFR, then H is determined in a unique way by a quintuple. We have two subgroups, H1, F sub 1, H2, F sub 2, and some isomorphism phi. Phi is isomorphism of quotient groups F sub 1 over H sub 1 to F sub 2, H sub 2. This is isomorphism, and xy belongs to H if and only if we have the following condition. This looks very strange, but if we look at this picture, in fact, we look at normal subgroups here in direct product between which contains SLFR. And this answer, in fact, is induced by the known, in some sense, description is connected with description of normal subgroup in direct product of groups. So this is
what is by I?